All right, everybody. Good to see everyone here. I'm sorry about the bit of the delay getting started, but we got there eventually. Okay. So as you can see, the subject for today, it's all about units and uncertainties. So we saw last time a little bit about the kind of extra things that we have to add on to numbers whenever we're considering them as scientific measurements. So we had to think about the number of significant digits, and very often it's useful to put the numbers in what we call standard form there, where we have that mantissa of the number between 1 and 10, and then we've got the power there. So that's what we did last time. And this week, the focus is these two extra things that we need to kind of team up with these numbers. So we need to add in some units and some uncertainties to really make it a scientific measurement. So that's what the lecture is all about today. Let's take a look at what's on the menu for today. So the plan is to start with, we're going to think about errors and uncertainties. We're also going to look at accuracy and precision. And that's all we need to think about for the time being about uncertainty, accuracy, and precision in scientific values. So from there, we're going to turn our attention to units. And once we get to units, there's a situation where there's a few kind of bits of formality, a few terms of the trade, a bit of jargon that we need to know when we're talking about units. So we need to know what we mean by a system of unit, what we mean by a type of unit. So is the unit what we call a base unit or a derived unit? And then there's this extra kind of type of thing that we call an SI prefix, which some people might say it's a unit, other people might not. For me, I'm going to say it's a unit. So that's the kind of basic plan for today. But as I said, I always like to start with some kind of picture which has a connection to what we're learning about today. Does anybody want to have a guess at what might be going on with this picture here and what the connection is to units? Any thoughts? Yeah. I think you're thinking along the right tracks here. So, of course, you need to understand units whenever you want to do something like launch a rocket. It's absolutely essential. This rocket in particular was launching what was called the Mars Climate Orbiter. So this was a mission on its way to Mars, going to study the climate of the planet. As we're going to see, things didn't go quite according to plan. So this is what the spacecraft looks like. So here it is. It's being tested out just before being launched. And it was manufactured by Lockheed. And when Lockheed do their engineering, the units they use are imperial units. So when they're measuring the amount of thrust that we're going to get from the spacecraft, the units that they use are called pound seconds. And that's what it is in imperial units. And that's fine, as long as you're consistent, as long as you use the same units throughout. But when the spacecraft got to NASA, NASA don't use imperial units, they use SI units. So we're going to learn what these SI units are and what these imperial units are. But the SI equivalent for the same thing, it's Newton seconds. And they're different by more than a factor of 2. So what happened? The rocket launched, it went all the way to Mars, and it was actually lost as it was entering the Martian orbit because of this mix-up with 2 units there. So I'd really like to emphasize that units are super important. And if you ever feel like it's kind of too bad if you lose some marks on an exam or something because you get the units wrong or you don't have units, just remember, it really can be a lot worse. So in today's money, this spacecraft, this whole mission, was worth about $500 billion. So, sorry, $500 million, $500 million. So clearly a big mission, and the whole thing didn't work because of this one mix-up in the units. Does anybody have any questions about that? Now you might say, okay, well, maybe I don't want to send a spacecraft to Mars. That's all kind of very long way away. In my kind of day-to-day stuff, in my studies, is that really going to be so important? So I'd like to share one more story where units got mixed up. So this was a story just back from 2015 in Northumbria University. So really not a million miles away. And the study involved a couple of sports science students. I think they were in their 3rd year. Has anybody heard of this study before? Okay, well, let's see what happens. So the study was on the effects of caffeine, about 300 milligrams. So a fairly substantial amount of caffeine, but not a ridiculous amount. So the idea was these two students, they were going to take this caffeine and see what happened, see how their physiology was affected. What actually happened instead? So the quote here, they were given 30 grams of caffeine instead of 0.3. So again, like I said, you might say, well, SI prefixes, not such a big deal. What's that little m? But clearly, you know, you don't have to be a chemistry student to see that that's a considerable amount of caffeine. There's another really interesting quote from this story that I'd like to emphasize. So it's this: the calculation had been done on a mobile phone with the decimal point in the wrong place. It's something that I kind of want to emphasize when I say, you know, it's really useful to get yourself a real calculator and not do calculations on your mobile phone. Because I think when you do calculations on your mobile phone, it's very easy to just be kind of a bit too hasty. You know, you've got all your notifications and you're swiping all around and you just do the calculation real quick, and it's very easy to make a mistake like that. So when you're doing calculations, I'd always recommend real calculators, much better. The other point I'd like to emphasize with this is that for a calculation like this, when we're moving decimal points around, you really don't want to be leaning on your calculator. This is something which your brain can do just as well as your calculator. And if you get something like, wow, that seems like a lot of caffeine, just because that's what your calculator tells you, just take a moment and you know, double check your math there. So let's see how much kind of caffeine this is in terms of cups of coffee equivalent here. So how many cups of coffee does 30 grams of caffeine correspond to? Let's take a look at the responses. Let's see what we've got here. Okay, so nobody's going for A. Clearly, it's more than 1 cup of coffee. Some people thinking maybe as much as 10,000, but the correct answer, it's actually C. So it's about as much as 1,000 cups of coffee. So very well done to everybody who gave that one a go, and especially if you got that one right. So even if you're a big coffee drinker like me, clearly 1,000 cups of coffee is far, far too much. Okay? So I can tell you that both the students who were involved in this study, they were fine. They did survive. They felt pretty buzzed for a few days, but they both made a full recovery with no lasting adverse effects there. But I do want to emphasize that when we're doing these calculations, it's not just academic. You know, these were 3rd-year sports science students. So in a few years, you could be getting involved with your own experiments, doing your own calculations, and it's really going to matter that you get the units right. Does anybody have any questions about that they want to ask? Any questions? Okay, so clearly this situation was a big mistake, and I think it would be fair to say this was a big error. But when we're talking about errors in science, most of the time, we don't mean something like this has happened. We actually mean something a bit more specific when we're talking about errors and uncertainties in science. So when we're talking about errors and uncertainties in the context of maybe a scientific research paper, error doesn't mean a mistake. So if when you come to hand in lab reports and they want an error analysis, that doesn't mean check your lab report for mistakes. It means that they want the uncertainties to be analysed there. So in this context, error and uncertainty are used synonymously. So there are some subtle differences between the two terms, but essentially they mean the same thing. They mean the uncertainty in the number. And this really just comes from the fact that every measured value in science has a range of uncertainty. I think it would be more straightforward if we just called this the uncertainty, but it's kind of stuck that this same thing is also very often called the error. So whenever you're talking about error analysis, or if someone says, oh, this paper's full of errors, they don't mean it's full of mistakes, they mean it's full of uncertainties in the numbers. And that's not because you've done anything wrong with your science, it's because every measured value intrinsically has a range of uncertainty. Now, there's a couple of different ways that we can express what this range of uncertainty is. And they're both fine, they're both equivalent. They're just two different ways of the same thing. So we can write our uncertainty as what we call an absolute uncertainty there. So I've just made up a number. So let's say x equals 7.6, just a totally made up number. And the range of uncertainty there, plus or minus 0.4. And then we've got the units there, centimeters. So maybe if you're measuring some distance and it's 7.4 centimeters, and then there's that range of uncertainty of 0.4 centimeters. And the plus or minus, that's just there to indicate that it could be as high as 7.6 plus 0.4 or 7.6 minus 0.4. So that's how you can write an absolute uncertainty. The other way you can write uncertainty is as a percentage. So here, this is exactly the same thing, 7.6 plus minus 0.4 centimeters, but instead of writing an absolute uncertainty where that is in the same units, we're writing the uncertainty as a percentage there. That's often quite useful when you want to get a general sense for the range of uncertainty in the value, and it doesn't matter kind of what the underlying value is there, to just have a percent uncertainty. How many of you have done standard deviations before? Maybe in science, math, statistics? Oh, okay, I guess that's maybe a bit more than half. So if you've done standard deviations before, usually these uncertainties will be one standard deviation. That's what they mean. Sometimes the uncertainty, so the thing that you say is plus or minus, sometimes it might represent more than one standard deviation. It might represent two standard deviation uncertainties. If you haven't done standard deviations before, that's absolutely fine. If you just want to think about this plus or minus bit as the range of uncertainty associated with that value, that's actually a pretty good way, it's actually a pretty correct way to interpret what that number means. Does anybody have any questions about this at this point? Hopefully that's fairly straightforward for now. So when we're thinking about uncertainties, a very important related concept are these ideas of accuracy and precision. And I think these are words that, they're kind of familiar and they're kind of used in everyday language. We want our results to be accurate and precise. But in science, these have two distinct, specific and different meanings. So it's important to be clear on what the difference is. So I mentioned on Monday that there was that NASA DART mission that crashed into the asteroid. And we actually use dartboards to illustrate these concepts. So I thought there was that nice connection there, because if you're that NASA DART mission, clearly you need to be accurate and precise. So I couldn't kind of resist drawing that comparison there. So that's the DART mission. But what does accuracy and precision actually kind of look like in terms of concepts when we're trying to unpackage them? if our measurement is accurate and precise, what that means is if you imagine a dartboard, that everything is right on the bullseye. So it's going to look something like this. If we get our dartboard in here, and then all the darts are right on the bullseye. So if you're playing darts, well, that's just some good darts. But scientifically, we'd say that those darts are accurate and precise. So we've got those two terms mixed up there. How can we see which part of that is accurate and which part is precise? So what's quite interesting, suppose you're playing darts and they all land close together, but they're off from the bullseye, so they don't all land on the bullseye. So they all look like this. So maybe your aim's just consistently off by the same amount. The way we use these terms in science, we'd say that both of these dartboards are precise because they're both consistent. They're both all hitting the same place. It's just one is off by a bit. So we would say that this dartboard, it's precise, but it's inaccurate. And that's really the difference between precision and accuracy. So you might wonder, well, if that dartboard is inaccurate but precise, what would something look like if it's accurate but imprecise? And it's really the opposite. So in this dartboard over here, which is precise but inaccurate, all the darts are neatly focused together, but shifted off from the bullseye. So if we're accurate but not precise, it's the opposite. So they're all centered around the bullseye, but they're not very tightly pinned down. So they look like this. So we'd say that this dartboard, it's accurate, but imprecise. So then you can probably see we've got a gap on our grid over here. So ideally we want to be accurate and precise, but sometimes we're neither. Sometimes it's just a big mess. And in that case, your darts are just all over the place. So this dartboard here, it's inaccurate and imprecise. That's the basic idea of what we mean when we're talking about precision and accuracy. Let's try a few questions and see how some of the factors might affect accuracy and precision. Let me get this question started here. Here we go. So suppose in our measurements we have what we call a systematic offset. Which of these ideas is it going to affect? Is it going to affect precision, accuracy? Maybe it's going to affect both, or maybe it's going to affect neither. If you've heard of systematic uncertainties before, then that might give you a kind of direct idea of what's going on. If you haven't heard of systematic offsets before, maybe have a chat with the people around you, or maybe just think about what would happen if all of those darts were systematically off. Let's take a look. Let's see what we've got here. Oh, okay, so people are mainly going for A and C, the precision and the accuracy. So I think you're on the right idea that it's only going to affect one of these more than the other so much. But the one it's mainly going to affect is precision. Okay? So remember, precision, that's the one where the darts, they're all together, but they're just kind of shifted off. They're shifted over from the bullseye. So very well done, everybody who gave a go, because the important thing with these questions is having a go. Okay, so taking your best shot at the answer. That's what really matters. And very well done to everybody who got that one right. Okay. Let's try another one a bit like this. Suppose we've got a random uncertainty in our measurements. So every time we make our measurements, there's some random uncertainty associated with it. Which one of these is a random uncertainty going to affect? Maybe it wouldn't affect either. Maybe it would affect both. So have a think about those dartboards and think, if there was more random uncertainty in there, which one is that going to affect? So again, if you're not sure, maybe check with the people around you. That's always going to be really useful, because I'm sure between all of us, we'd be able to figure all of these out every time. Okay, let's take a look. Let's see what the answer. Okay, so most people think it's going to affect precision and accuracy. Okay, and I can see you're thinking there. Let's see what the result is. So it's only actually going to affect accuracy, because if we have some element of randomness in our measurements, that's not going to preferentially move us one way or another. It's just going to add more scatter to where those dartboards are landing. But it's not going to be that situation where we had all the darts together, but just shifted away from the bullseye there. So random uncertainty affects accuracy there. So very well done to the people who got that one. It's a bit of a trickier one there. And like I said, very well done to everybody who gave the question a go, because that's the important thing there. So these two things, a systematic error and a random error, these are the two big classes of uncertainties that you might get when you're doing an experiment. So you might get some systematic error and you might get some random error. There's one other big class of error and uncertainty that we need to think about. And if you're a statistician, then maybe, strictly speaking, it's not a kind of formal kind of uncertainty, but it's a really important one to think about. So suppose we've got human error affecting our results. Which one of these could be affected by human error? So maybe you're doing an experiment and you're timing how long something takes. That's going to introduce an element of human error, because you're relying on a human to time how long something takes. So have a think about how could that affect our measurements? How could that affect our accuracy? How could that affect our precision? Let's take a look at what we've got here. All right, okay. So it looks like most people are going for both of them there, okay? So well done everybody who gave that one a go. And that's the correct answer there, B, okay? So a human error could affect both our accuracy and precision. So if we just think about something being timed, they're not going to be hitting the stop button on the stopwatch at the exact time for every event. There's going to be some randomness there. The other thing you might find is that maybe some people, they're consistently slow with stopping that stopwatch there. Maybe they're just not paying quite too much attention. Or maybe some people, they're just a bit too fast with pressing the stop button on the stopwatch. So that's going to introduce a systematic effect in your measurements. So there are these two things that we have to think about could be affected by human error. So whenever you have a human in part of your data collection, in part of your experiment, we've got to remember that they could be affecting the accuracy and the precision of our results. Does anybody have any questions about that at this point? So if there's no questions, we can move on for now. So I really try and minimize the amount of jargon and technical terms when we're talking about physics, because very often it can be a distraction. But when it comes to units, there are a couple of things that we do have to be pretty sure about what we mean when we're talking about these things. So we have to know what we mean by a system of units, and we have to know what we mean by types of units, because we can get different types of units. And these are two different things. Now, I found it very difficult to come up with a definition of a system of units that didn't have the word system in. So that wouldn't be kind of particularly useful as a definition. So I thought what would be best is to show you guys a few different systems of units. And then I think you really you see what's going on here with what we mean by a system of units. So a system of units, it's really that situation we saw at the beginning with NASA and Lockheed and trying to launch that satellite to Mars there. So what we mean is maybe if we're talking about imperial units, if we're talking about pounds and yards and Fahrenheit, these are all part of the same system of units that we call the imperial system. Does anybody like the imperial system? They use the imperial system? Not so much. Okay, okay. It's still widely used in the US, of course, which is part of what can lead to a mix-up like that. So that's one system of units. The system of units that we're going to use in physics and which is almost universally used in science is what's called the SI system. So this is whenever you're using kilograms, meters, and Kelvin. And there's several other units, but those are just a few examples. Does anybody know what a Kelvin is a unit of? Yeah? Absolute temperature, yeah. And so we had someone over there as well? Temperature, yeah, very good, okay. So Kelvin, it's a unit of temperature. And it's directly related to Celsius that you might be more familiar with. But as you said, it's just shifted by an amount. So we're going to learn a lot more about that when we come to do thermal physics. Does anybody know any other systems of units aside from the SI system and the imperial system? Any other systems of units? So there are a few more. If you end up going down more the kind of theoretical physics route, there's a system that theoretical physicists like to use called natural units. And what they do is they take all of the fundamental constants that we use in physics. So I've got the speed of light there, c, that big G there, Newton's gravitational constant. We're going to learn about the h there, that's Planck's constant. They take all the fundamental constants of nature and they say they're just equal to 1. So all of their values, they come out to kind of strange numbers. If you actually want to convert them back into something physical, you have to put the values back in. But that's something that theoretical physicists use. And really what it means is it saves them having to write out all of the C's and H's and G's in their equations. We're not going to use natural units in this course, but it's useful to have an idea what they are if people are talking about. And it helps to illustrate what we mean by a system of units. So this is what we mean when we're talking about a system of units, when we're saying you have to be consistent with the system of units that you use. The other kind of thing that we talk about are types of units. And this is really, really important in physics when we're talking about types of units. And there's 3 main types of units that we see in physics. The first type of unit that we're going to see very often throughout this module, it's called a derived unit. A derived unit is a unit which is made by combining other units together. Can anyone think of any examples of a derived unit? Yeah. Very good, yeah. So we had the Newton there. We're going to learn about the Newton very soon if you've not already done that. Can anyone think of any other derived units? Yeah. Pascal, great one, great one. Units of pressure, really great example. Any other examples of derived units? Yeah. That was great. I was kind of hoping someone would say meters per second. Thank you. Yeah, so probably one of the simplest derived units that you can get is the unit for speed. Okay, so we've got meters per second, the derived unit for speed. Or if you don't like SI units, maybe you want to think about, miles per hour. If your speed is 50 miles per hour, you've got those units of miles per hour. So we'd say miles per hour, mph, that's a derived unit. So you can explain what a derived unit is by deconstructing it into constituent parts. So I was really glad someone mentioned meters per second, because that really brings us on to perhaps the most important kind of unit for physics, which are the base units. So meters and seconds, these are two examples of what we mean by a base unit. These are units which are fundamental, and you can't break them down, you can't describe them in terms of other units. They're just, in a sense, fundamental. So if we said, what's the units of speeds, meters per second, great. We can say, okay, well, that's made of meters per second. But if we said, well, what's a meter made of? We can't really break that down anymore. I mean, you could say, well, it's made of centimeters, but that's just kind of circular there. So base units, they're fundamental. We can't describe them in terms of other units. So those are two big kinds of units there. The third type of unit that we're going to see a lot of are what's called the SI prefixes. Now, some people say they're not really units because they just change powers of 10. Can anyone think of an example of an SI prefix? Yeah. Kilo? Yes, great. And centi? Yeah, very good. Any other examples? Nano. Oh, that's a great one. That's my personal favorite. Yes. Any other? Yeah. Pico. Great. Really good. And we'll have one more here. Hector. Oh, that's a great one. We got some really good SI prefixes. Now, some people say they're not really units because, strictly speaking, they're numbers. They change things by powers of 10 here. Personally, let's not worry too much about the semantics there. I think we can include the SI prefixes as units. Let's take a quick look at the SI prefixes that we might see. So we had pico mentioned and exa. Or maybe this chart doesn't go all the way up to exa. That's even even higher. One more. Okay, so well done for mentioning that one. That's really good. And then we've got centi on there. So the important thing to remember with these SI prefixes is that they just represent a number, and that number is always 10 to the power of some other number. So if we had nanometers, that just means 10 to the minus 9 meters. The other thing you might like to do with SI prefixes, so remember last time we said, you want to write your numbers in standard form, so some mantissa times 10 to the power of some number. Well, if that 10 to the power of some number happens to be one of these numbers that we have an SI prefix for, then it's really nice, it's really professional to, instead of writing the 10 to the power, you can write the SI prefix. So suppose your power of 10 is 10 to the minus 6. Well, 10 to the minus 6 micro, you can just write that little micro there instead of 10 to the minus 6. And then your work looks really sciencey and professional. So I would recommend doing that. There's no need to memorize all of these. You'll become familiar with some of them just through working with them, but we don't need to memorize them. It's just useful to have an idea what they're about. Does anyone have any questions about the SI prefixes? We had some great examples there. Let's just keep an eye how we're doing for time. Okay, so the last thing that I'd want to tell you guys about today is a little bit about where we get the base units from, where these fundamental units are from. Oh yeah, we'll just try this quick question first before we move on. So we'll try this calculation. What is 656.28 in standard form? So there's a few things we need to do because the 656, that's not in standard form to start with. And then we've got the nano there. So remember, nano is 10 to the minus 9. Let's see what we get here. Oh, okay, so nobody's going for A. Nobody's going for A. We don't like that 10 to the minus 5. But these look pretty evenly split between B, C, and D. Now, I can see why you might be going for C, because that is 10 to the minus 9. We do have that 10 to the minus 9. But if we look here, so that's 6.56 times 10 to the minus 9, whereas the original number is 656. So if we just replace that nano with 10 to the minus 9, we've not quite done the whole thing there. So we've got to then take that 600 and we want to scale it so it's between 1 and 10. And when we do that, we get that the correct answer is this 10 to the minus 7 there. So very well done, everybody who got that one. It's a bit of a tricky one. We'll have some more practice with this in the workshop. Okay, so the last slide I want to share with you guys for today, it's just a little bit about where these units come from, okay? And I think you can informally divide these units into 3 different situations here. So you've got what I call the classical era, when these units were first defined, and then what I call the industrial era, and then the modern era, the information era. Now you might say, well, hang on, I didn't sign up for a history degree. I don't really want to know about the history of these units. I just want to know what they are now. But it's important to know where these units came from so that we can understand the modern definitions of what these units are. Because if you just look at the modern definitions, you'd say, well, that seems really arbitrary. Why would you ever define a unit like that? But if you see where they come from, then it makes sense. So let's start with the meter. And this was kind of formally defined towards the end of the 1700s. Does anybody know how the meter was originally defined? So it was defined, have you got the answer there? It was defined in terms of the planet Earth. So it was the distance from the pole of the Earth to the equator divided by 10 million. So like I said, it's based on planet Earth. Once you've got a unit for length, you can define a unit for volume. And the unit that they use in this system is the litre. And once you've got a litre, you can then define mass. So the kilogram was originally defined as the mass of 1 litre of water. So it's a really nice way of defining mass, because you start with the length, and then you can construct a litre, and then anyone can fill up that litre with water, and then you've got yourself your very own kilogram. We've also got Celsius, and that was based on the boiling and the freezing temperature of water divided by 100. And that gives us the Celsius. And then the last unit from the kind of classical era, it's of course time. And time was originally defined by the rotation of the Earth. So the second, we had 60 seconds, 60 minutes, and 24 hours gives us 1 day. And that's where we got the second from. So those were the original definitions of the base units. The problem was, by the time you get into the industrial era and you want to start making trains and factories, these units, they're not consistent enough. They're not the same every time if you want to make a steam engine or something like that. So what we found, once we start to enter the industrial era, is that units were defined differently. So for the meter, instead of having this distance here, they just said, here's a platinum bar, and this platinum bar is 1 meter. That's the definition of a meter. So if you're twice as long as that, you're 2 meters. And then they did the same kind of idea with mass. So instead of saying the mass of a litre of water, they just said, well, here is a platinum cylinder, and this platinum cylinder is 1 kilogram. If you want to make your own kilogram, you've got to ask them very nicely if you can borrow theirs and calibrate your kilogram against them. And that's really the issue with this industrial era of units, that they're all based on specific objects. So if I said, look, I'd really like to do a physics lab for this module, can we borrow the the standard meter for a bit and take some image, you know, they're going to say no thank you. And that's part of what motivated defining units in what I call the information era. So in this era, the modern era of units, all units are based on information. You can write down the definition of a unit based purely on information, and it doesn't rely on any physical objects. And it's a really important way of approaching units because it's reproducible. And it kind of gets back to what was so good about the classical era of units, that in principle anybody could reproduce them. So if you look at how the meter is defined now, it was changed in 1983 to be based on the speed of light. So we now define the speed of light as a fundamental fixed constant. And we say that the meter is how far light goes in 1 over the speed of light of a second. We take the similar kind of idea with other units. Now, I just want to emphasize with these other units, they're really kind of thorny, convoluted descriptions here. So I'm only really kind of showing them here just for kind of illustration. So please don't worry too much about all the details. I really just want to show them to kind of illustrate how we now define modern units. So with the kilogram, until very recently, the kilogram was just the mass of this platinum cylinder. Now the kilogram is defined as the particular mass, so that Planck's constant comes out at this exact value here. So we're going to learn about what Planck's constant is next semester. Let's not worry too much about all the details of this. All I'm saying for now is that we define mass in terms of an experiment that someone can perform, that in principle any of us could go and perform. And we set our mass so that Planck's constant comes out at this exact value, and then we've got ourselves our very own kilogram. And you might say, why that particular value? And it's so that we get back to the kilogram as originally defined there. So then the last unit that we need to think about for today is the second. So whereas it was originally based on the rotation of the Earth, it's now based on cesium atomic clocks. And it's specifically 9 billion and something periods of radiation from a specific isotope of cesium, cesium-133. And this is the point I want to emphasize with this, that you might say, well, why 9 billion, 192 million, the whole thing? Why not just, 10 billion? That would, make it a round number, make it a lot easier. And the reason is, with all of these units, to get back to this original definition, they have to match the original definition, but in a form that's going to be more precise and more reproducible. Does anybody have any quick questions about that? Okay, well, that's all I wanted to show you guys for today. So sorry we had a few technical difficulties. Just a quick reminder, we got the workshops tomorrow, and you're going to need a textbook for the workshop. So if you don't already have a textbook, make sure you get one from the library, okay? But that's all for now, so thank you for listening, and I'll see you all next time.